Hello maths fans, Dr Tom Crawford here at the University of Oxford to teach you some more calculus. Today we're going to look at the separation of variables technique for solving first order differential equations. This technique can be applied whenever we have an equation with the following form. So being first order, we will have a single derivative, dy by dx, where y is a function of x. And we want this to be equal to a function a of x multiplying a function b of y. The name of the technique, separation of variables, gives you a very big clue as to what we do next to try and solve this equation. And what we want to do is to bring all of the y terms over to the left-hand side of the expression and all of the x terms over to the right-hand side, and then we integrate both sides. So here, this means dividing by b of y, and then we want to leave the dy term, so that now becomes an integral with respect to y. And then on this side, we take the dx across, i.e. we integrate both sides with respect to x, and what we're left with is the integral of ax dx. So this equation now contains two integrals, and the hope is that we know how to integrate 1 over this function of y, and we know how to integrate the function of x. And if we can do this, we will have an implicit equation involving y and x, and then we can rearrange to get y equals something which will be the original solution to our differential equation. Something that I find helpful when using this technique is to think of our derivative here, dy by dx, to kind of treat it like a fraction. Now, I know the pure mathematicians amongst you, those of you who have studied analysis and limits, will be thinking, can we really do that? It turns out we can, but for the purposes of solving calculus problems, we don't really worry about exactly why we can do it. We just say, well, if this is a fraction, then what I'm doing here is multiplying both sides by dx in some sense, remembering you have to integrate, and then you're left with the dy by itself, and again, you have to add in the integral sign for it all kind of to make sense. A final point to mention here is that b of y, of course, has to be non-zero. We still can't divide by 0, but in the case where b of y is equal to 0, this equation will just reduce to be equal to 0 when b of y is 0. And so what we're actually solving is dy by dx equals 0, so that gives you the solution y equals constant. So if b of y is 0, the solution is just y equals constant, because a constant differentiates to give 0. If b of y is non-zero, which is what we're going to assume from now on, if b of y is non-zero, then we proceed like this and we integrate both sides. For our first example, we're going to look at the following. dy by dx is equal to y divided by 1 plus e to the power x. So using our general form that we just discussed, our function here, a of x, is going to be equal to 1 divided by 1 plus e of x, and b of y is just equal to y. So we could now just plug these into our formula and then integrate, or as I prefer to do it, I just think about taking all of the y terms over to the left-hand side. So here we have to divide both sides by y, so I get 1 over y. Then I'm going to have my integral dy, and I'm going to multiply up by the dx, or integrate both sides, I should say, with respect to x. And what we get over here then is 1 over 1 plus e to the x dx. And you'll see this is the same as that general form that we discussed, because this is the integral of ax, and this is 1 over b of y integrated. Integrating the left-hand side is quite straightforward. This has come from log of y, and I'm going to put my plus c here. Remember, in these problems, you only have to use plus c once, because you would get a constant on both sides, so we can just combine them into a single constant. So I'll put my plus c here, and then this is equal to now the integral of 1 over 1 plus e to the x dx. Now, in order to do this x integral, we have to think a little more. This is indeed possible to integrate, but we have to be clever. And what we want to do here is actually rewrite this as 1 plus a fraction, or possibly minus a fraction, as it will be in this particular situation. The motivation for doing this comes from the fact that I want to be able to integrate the denominator. And it kind of looks like it may have come from a log. So similar to here, we had the 1 over y goes to log of y. We've got 1 over something, so we kind of want it to go to log of that something. But when you differentiate log of a function, on the numerator on the top, you get the derivative of the function inside the log. So here we need an e to the x on the top. And of course, we don't have it, which looks like a bit of a problem. However, if we were to rewrite this as 1 minus something, we can integrate 1, and the minus something, it turns out, has the e to the x on the top. Now, there's no foolproof method of knowing to do this. You kind of learn through familiarization with these integral type problems, and separating out the fraction into 1 plus or minus something can be very helpful. So what we have is going to be the integral of 1 plus e to the x minus e to the x. So I've added and subtracted the same term, and then this whole thing now is over 1 plus e to the x. So now we've got a 1 term at the beginning minus something that we can integrate. So this becomes the integral of 1 minus e to the x divided by 1 plus e to the x dx. And now we've got the e to the x on the top, which is like the reverse chain rule of the denominator. So this will integrate to give a log, this will integrate to give an x, and then we can put it all together and solve for y. Doing the actual integration now, this will give us x. I don't need my plus c, remember, because I've already got it on the left-hand side. And then that's going to be minus the log of 1 plus e to the x, like so. And we can just double check. If I were to differentiate this log, I'd get 1 over the thing, 1 over 1 plus e to the x, multiplied by the derivative of the thing, which here is just e to the x. And then I got the minus sign, so it all does check out. Now, we've got log of y plus c equals x minus this. What I'm actually going to do is take the c across. So if I do minus c here, then I can put log of y here. And now I'm going to exponentiate both sides. So take e to the power of the left-hand side and e to the power of the right-hand side. And we want to do this to remove the natural log, because of course e is the inverse of natural log. So this will give me y equals e to the x multiplied by e to the minus log 1 plus e to the x multiplied by e to the minus c. And the reason I've written these as products of these e's is, of course, when you have the product with some indices, you just add the indices together. So I've just split it up to these 3 separate terms. Now we can simplify this. This minus can go inside the log here using the powers or the properties of logs. And then this, I'm just going to call this whole, this is still a constant, which is undetermined. So I'm going to call this a as my undetermined constant, playing the role of that plus c. And so now my final answer will be y equals the e and the log cancel. So I've got e to the x times that a, and then the whole thing is divided by 1 plus e to the x. So this, I believe, should be the solution to the original first order differential equation. And we found this using this technique of separation of variables. It's of course always good practice to check your answer. Unfortunately, we can do this using the Maple Calculator app. So I have it here on my phone. I can open up the camera and I can take a photo here of my function at the bottom, y equals a e to the x over 1 plus e to the x. And then within the app, I can actually check and click differentiate with respect to x, and it will give me the derivative. From the Maple Calculator app, I can see that the derivative here, dy by dx, is equal to a e to the x over 1 plus e to the x minus a e to the x all squared divided by 1 plus e to the x squared. So this has calculated the quotient rule for me based on this being my function y. To check that our answer is correct, we of course need to rewrite this in terms of y to make it look like our original equation. So we do that by putting this over a common denominator. So this will become a e to the x times 1 plus e to the x minus a e to the 2x, because the squared there of course becomes a 2x in the power, all divided by 1 plus e to the x squared. So now we can see this term here will cancel with this, and what I'm left with is a e to the x divided by 1 plus e to the x all squared. That's exactly y down here with an extra term on the bottom, 1 plus e to the x. So checking the derivative here, we can see that this is indeed correct. And so the solution that we found with the help of the Maple Calculator app, we can verify this is the correct solution. It satisfies our differential equation. Our second example is going to be a little trickier because at first it doesn't look like it's in separable form. So we're going to consider dy by dx is equal to sine of x plus y. Now there are a couple of different ways of approaching this problem, but the important thing to remember is we need this to be a function of x multiplied by a function of y. And here, of course, we have a function of both x and y sort of trapped inside the sine function. Now you could proceed using the addition formula, and that might help to separate things out, and you could continue from there. However, the way I'm going to approach this is using a substitution. So what I'm going to do is let u, which is a function of x, be equal to x plus y, where y, of course, is a function of x. Now, if I calculate du by dx, always helpful when you're doing a substitution to know its derivative, this is 1 plus dy by dx. And so therefore, dy by dx is equal to du by dx minus 1. So I'm going to put that in. So dy by dx is now du by dx minus 1, and that's equal to sine of u. Now I'm going to add 1 to both sides. So get rid of that, put the plus 1 here, and now it is indeed in separable form. I have a function of u, I've got my du by dx term, and then my function of x here is just the constant multiplying everything, which is 1. So I'm going to take the function of u, bring it over to the left. So I get the integral of 1 over 1 plus sine of u integrated with respect to u, and that's got to equal the integral dx, which of course we can just do now is x plus c. So my integration constant is here, so we don't have to worry about it on this left-hand integral. Now the tricky part, of course, is doing this integral, because it's not immediately obvious how to integrate this function. And like before, we're going to have to think a little bit. So here, what we actually want to do is multiply the top and the bottom by 1 minus sine of u. So this is going to now become the integral of 1 minus sine of u, and then on the bottom I've got the difference of two squares, which gives me a 1 minus sine squared of u du. Now the reason this is helpful to get the difference of two squares on the bottom is this, of course, is equal to cos squared. We have our famous trig identity, sine squared of u plus cos squared of u is 1, so 1 minus sine squared is cos squared. So we can say this whole thing is in fact equal to 1 divided by cos squared. That's my first term. And then the second term is going to be minus sine of u divided by cos squared of u. So there I've done an extra step in splitting this up. I've substituted 1 minus sine squared is cos squared, and then I've split it up into two separate fractions. Now hopefully some of you may have spotted the two terms that we're left with as individual integrals we can actually do immediately through direct integration. Now these are not necessarily easy to spot, so I'll help you out. The first term here, 1 over cos squared, is of course equal to sec squared u. And what function differentiates to give sec squared? Well, that's just tan. So this first one integrates perfectly to give tan of u. Now the second term is a little trickier. It's kind of similar to what we did in the first example, but instead of it being the log of something having been differentiated, what we've got here is a power of some function on the bottom, but on the top we've got the derivative of the function on the bottom. So this whole thing has in fact come from cos of u to the minus 1, or minus 1 over cos of u. Because if you differentiate this, you bring down the minus to get a plus 1 over cos squared, and then the chain rule says you multiply by the derivative of cos, which is minus sine. So you can check if you differentiate minus 1 over cos of u, you will indeed get minus sine of u over cos squared. So the integral of 1 over 1 plus sine of u is actually equal to tan of u minus 1 over cos, or tan of u minus sec of u. Now that we've solved this integral, we can plug in our solution, and this of course is equal to the right-hand side, which was just x plus c. Now the final step, of course, is to remember we made this substitution, that u was equal to x plus y, so we cannot leave the u in our solution. So we substitute back, and we can say that tan of x plus y minus 1 divided by cos of x plus y is equal to x plus c. And we can in fact tidy this up through one final step. If we multiply through by the cos term, tan of course is sine divided by cos, so the very final simple solution will be sine of x plus y minus 1 is equal to x plus c multiplied by cos of x plus y. And you'll notice that this is actually what we would call an implicit solution. We cannot rearrange this, or not easily, to get y equals something. We've got x and y kind of trapped inside the sines and the cos terms. As with our first example, we of course should double check that this is indeed a solution to our original differential equation. And here, because of the implicit solution, we're going to have to use implicit differentiation. So if I differentiate sine, that will give me cos of x plus y, and then the chain rule says I have to then multiply this by the derivative of the thing inside sine. So here we differentiate with respect to x, and that's 1 plus dy by dx. 1, of course, disappears when we differentiate with respect to x, and this whole thing is equal to, let's do the first bracket, so x plus c, if we differentiate that, we get 1, multiplying the cos term. And then if we leave the first bracket alone and differentiate the cos, I'm going to get a minus x plus c sine of x plus y. And again, the chain rule says I have to differentiate inside. So this second term is multiplied by a 1 plus dy by dx. So it's a pretty complicated expression. And what we need to do now is rearrange to get dy by dx on its own and have dy by dx equals something. And hopefully that something will turn out to just be sine of x plus y. So the first thing that I can spot here is that we can cancel this cos x plus y term, because you have cos x plus y times 1, and then you have cos x plus y. So this 1 cancels with this cos x plus y. And now if we group together the derivative terms, what I've got is dy by dx all multiplied by cos of x plus y. And then over here, if I take this across, I've then got a plus x plus c sine of x plus y, multiplying the derivative, and then I'm left with the other term, which means this whole thing has to equal minus x plus c times sine of x plus y. Now that we've factored out the dy by dx term, we can divide by this and rearrange to get dy by dx equals something, which hopefully, fingers crossed, we can get to look like sine of x plus y. So I believe we're going to get dy by dx equals minus x plus c times sine of x plus y, all divided by cos of x plus y plus x plus c times sine of x plus y. This still looks quite messy, so what we're actually going to have to do now is try and use our original solution, the implicit form, to try and eliminate some of these terms. Now, there again are several ways to do this. What I'm going to do is try and replace x plus c in here with coses and sines, because I feel more confident using my sine and cos identities, and hopefully things will cancel out and give me this nice, fingers crossed, simple solution. So if I replace the x plus c in here, what I should get is dy by dx is going to be equal to, so x plus c is going to be this sine thing over cos. So this is now minus, I've got the sine x plus y, I'm then going to be dividing by the cos term, and then on the top I've also got sine x plus y minus 1. And then on the bottom, I'm going to have the cos term here, and then the x plus c is going to be similar to the above, so I've got plus the sine term, that's going to be divided by the cos term, and then multiplied by this sine of x minus 1. Now again, this might not look simpler, it probably looks more complicated, but I can already see what's going to happen, and I think this is going to work. Because what we can do now is multiply the top and the bottom by the cos term. So we lose the cos term here, this becomes a cos squared, and then this term disappears. And now, if I just expand this out, what I've got is a minus sine squared plus sine. So minus sine squared x plus y plus sine of x plus y on the top. And then on the bottom, I've now got a cos squared plus a sine squared, which is 1, and then minus a sine xy. So we get a 1 minus sine x plus y. Now I'm aware I'm going quite quickly through this, mainly because implicit differentiation and trig identities are not the main purpose of this video. But as I said we were going to do this, I'm going to stick at it and we are going to make sure that we get the right answer. Always good to check your work, no matter how long it may take. So here we've actually got the answer now, because this thing over here, we can actually factor out a sine on the top. So you've got sine of x plus y on the top, and then in the bracket you've got 1 minus sine, which cancels on the bottom. So the final answer is sine of x plus y, which is what we had up here. So dy by dx is sine of x plus y. Our implicit solution here is indeed correct. So there we have it, a couple of different examples showing you how to use the method of separation of variables to solve some first order ordinary differential equations. Remember, the first step is always to make sure your equation is in the correct form, which here means dy by dx must be equal to a function of x multiplied by a function of y. And as we saw in our second example, you might have to make a substitution in order to get it in this separable form. But then once you do, we take all of the y terms over here, all of the x terms over to the other side, and hopefully we can then integrate. If you'd like to keep practicing the separation of variables technique, make sure you check out the worksheet I've created in Maple Learn, which you can try for free by clicking on the link in the video description. Have fun. As always, thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all soon. Take care.